Structure of cesium chloride. The unit cell of cesium chloride is shown in figure 19. In the structure, cesium ions are represented by the solid circle, where the chlorine are represented by the hollow circle. The silent feature of cesium structure is chlorine ions are arranged in the simple cubic arrangement. In this, chlorine ions are present at all the corners of the cube. The cesium ions occupy the cubic side. Cesium positive ions present at body center of the cube. It is clear that there are 8 chlorine ions corner of the cube. Each of the ions shared by 8 unit cell. It contributes per unit cell 1 by 8. Therefore, 8 chlorine ion at the corner is 1 chlorine ion per unit cell. There is also one cesium ions in the body center, and it contributes per unit cell is 1, and the cesium ions there is 1 chlorine ion, so the stoichiometry is 1:1. The CaF2 structure may be defined as the structure arranged in CCP arrangement. In this arrangement, Ca plus 2 ions are present at all corners and thus at the center of each face of the cube. Fluoride ions occupy all tetrahedral sides. There are 2 tetrahedral sides per atom in closed packed lattice. This means that there was 2 tetrahedral sides of every Ca positive ions, and since F negative ion occupy all tetrahedral sides, there will be 2 F negative ions of each Ca plus 2 ions. Thus, the stoichiometry of compound is 1:2. In this structure, each F negative ion is surrounded by 4 chlorine ions, which are disposed together. The regular tetrahedron, on the other hand, each Ca plus 2 ions is surrounded by 8 F negative ions, which are disposed towards the corner of a cube. Thus, the coordination number of Ca plus 2 and F negative ion are 8:4. The structure is adopted by a large number of fluorides such as CuF2 and BaF2. The summary of the structure of ionic solid is given in table 1. The radius effect, ratio effect, and coordination number. The radius ratio is important parameter to predict coordination number from the relative size of ion and the ionic structure. Ionic solids are made up of cation and anion, which are definite arrangement. Each of the ion is surrounded by a large number of opposite charge. For example, ionic crystal of type A positive, B negative ions are surrounded by a definite number of B negative ions. This number is called coordination number of A positive. Similarly, A positive ion which is surrounded by B negative is called coordination number of B negative ion. The arrangement of ion in a crystal and number of ions depends upon the relative size of the ions and the ratio of radii of the ions. The ratio of radii of positive and negative charge is known as radius ratio. The radius ratio plays very important role in determining the structure of ionic solid. Let's consider how the radius ratio changes the structure of compound. Consider the table structure in which all anions are touching each other and they contain simultaneously octahedral arrangement, but 4 are shown clarity. Now if we decrease radius ratio either by decreasing the size of cation or by increasing the size of anion, the structure will become unstable. All ions will stable to touch simultaneously cation. In order to touch the cation, anion to go closer and closer, therefore repulsion will increase. When the radius ratio further decreases, the stage will appear when one or more anions may be pushed away, so the remaining ions fit around the cations, giving more stable structure. In other words, there may be change in coordination number from 6. Alternatively, if we increase the radius ratio either by increasing the size of cation or by decreasing the size of anion, the structure will become unstable. All ions will no longer be touching one another. If the radius ratio is further increased, the ions will going further apart. Consequently, a stage may reach when more number of anions may be able to fit around the cations, giving more stable structure. In other words, there will be a change in coordination number of 6 to 8. This means there is a upper and lower limiting radius ratio of which coordination number 6 is stable. It has been calculated the octahedral coordination number 6 is stable for the radius ratio 0.414 to 0.732. That if the radius ratio is in the range only, then cation will be able to keep 6 anions in contact. If the radius ratio less than 0.414, coordination number will decrease to 4. More than 0.732, the coordination number will increases. Similarly, the radius ratio ranging 0.225 to 0.0 Similarly, when radius ratio range between 0.51555 to 0.225, the diagonal sides were performed in coordination number cation is 3 and studied in table given. Application of radius ratio rule may be illustrated by the following example. The radius of Na positive ion is this and the chlorine ion is this. And the radius ratio is this. The ratio lies between 0.1 and Na positive bracket octahedral sides. The radius ratio of a respectively radius ratio. Limitation of radius ratio rule. The radius ratio rules applies only to packing hard sphere is called of a non-size. This is far from reality. Anions not hard but are polarized influence under influence of cation. The extent of polarization of an ion leads to be covalence and result in serious error in the application of radius ratio rule. For example, radius ratio 1.11 to 2.6 indicates coordination number of 6 by actually AGI is 4 coordination number tetrahedral zinc plate structure. Many serious errors occur by coordination number 6 versus 8. Coordination number of 8 is found only in cesium chloride, cesium bromide, cesium iodide. Although radius ratio calculation predicts cesium chloride coordination number 8. Structure of oxide for large divalent metal such as Ba plus 2, Sr plus 2, Pb plus 2, yet no 8 coordination oxide MO had been observed. Radius ratio rule fails to explain why compounds crystalline is more than one modification have different coordination number. For example, thallium chloride crystalline to form adopting NaCl structure having coordination number 6 with internuclear distance. The effective radius ratio of cation is greatly influenced by the anion, so that the radius ratio changes. For example, AgF and NaF crystalline out in NaCl type structure with coordination number 6. Now we assume the size of fluorine ion remain constant, then Ag positive is bigger than Na positive. On other hand, for a given size, chlorine ion is AgCl and NaCl size of cation are reversed. Na positive is bigger than Ag positive. Internuclear distance between M and X is a angstrom in angstrom. It is also true for their bromides. This understanding because Ag positive ion is softer than Na positive and introduce relatively more covalent character with polarizable anions like Cl negative and bromine negative. These changes in size of cation may introduce error in the radius ratio rule calculation and prediction. Thus, the radius ratio rule calculation are very easy for predicting coordination number of ionic or particular or partially ionic compound, but such predictions can be misleading when atomic and ionic radii are not well defined.